We are very pleased to see you back because the picture sent to represent their team was taken a few years ago in the Musée de l'Air et de l'Espace because the team took part to a previous challenge. They are coming from Universidad Rey Juan Carlos, and they are going to speak about mission profile and concept for a high-speed, long-range suborbital transport vehicle. The floor is yours.
Thank you so much. All right. So my name is Alondra, and it's my pleasure to present Project STEINER for Work Package 11, Mission Profile and Concept for a high-speed, long-range suborbital transport vehicle. We decided to use a systems engineering approach to solve this problem, with coordination between various design sections to find the optimal solution. We proposed the following methodology. First, we define the mission requirements and constraints. We move on to and select hypotheses and models. Using this initial work, we make the preliminary vehicle design with several different subjects, as we will see. We find the optimal trajectory profile and guidance, navigation, and control system, and finally define the vehicle architecture. So to work, the first thing we had to do was define the mission statement, a clear and concise mission statement, which in our case was given by the challenge guidelines, to design a long-range, high-speed suborbital vehicle capable of regular transport of civil passengers and associated cargo. From this point, we can define the mission requirements for safety, range, and flight time, which give a numerical definition to the abstract mission statement. Finally, the constraints are deduced from the requirements, and this allows us the boundary conditions to begin our design work. The second portion of the preliminary work was to select the hypotheses that we would take into account, as well as the environmental models. This was very interesting because the complexity of the hypothesis, more complex hypotheses in general increase the accuracy of the solution. However, they make the design process more difficult. So we had to find the sweet spot for each of these cases. For example, in the gravitational model, since we had assumed a non-spherical Earth, we needed to introduce the J2 parameter of oblateness instead of the usual point mass gravitational model. For the atmosphere, we selected the usual international standard atmosphere model, which gives pressure, density, and temperature as a function of flight altitude for the entirety of the flight. All right, so now we start the actual work once we finish the initial preliminary work. For this, we chose 9 key areas of study. Each one of them had implications not only on the final vehicle design, but also on each other. So it was a very iterative process between all of these different subjects. My colleagues Daniel and Sergio will now explain each of them and how their conclusion impacted the final conceptual design of the vehicle.
During its flight, the suborbital vehicle is under varying aerodynamic conditions. Thus, there are defined different zones of interest over the wing, coexisting subsonic and supersonic airfoils. Firstly, for the subsonic conditions, the airfoil has been designed by the linearized potential theory. Here, the problem was to pass the transonic issues without difficulties, needing a transonic airfoil. The one above is the theoretical optimized airfoil, while the one below is the approximating NICA airfoil. A supersonic airfoil was chosen for achieving not only the supersonic flight conditions successfully, but also taking into account the re-entry phase. Therefore, the thickness was maximized inside the aerodynamic possibilities in order to obtain a thicker structure. Finally, the 3D shape of the vehicle was optimized for supersonic flight, minimizing the huge increase of drag. Moreover, the wheelets were also defined to minimize the transonic effect on the structure. The nominal supersonic and hypersonic flight regime forces the vehicle to undergo aerothermal effects, showing a wider variety of phenomena such as divergence or fluttering. However, the problem is hard to be solved analytically, and only preliminary conclusions can be made without introducing complex software. The re-entry is one of the most critical phases in which the integrity of the structure is tried out. Due to the hypersonic speed and the increment of air density while descending, the vehicle receives a high heat flow from the boundary layer. This heating is spread in the vehicle through the nose cone and leading edges. As the vehicle increases its surface temperature, the temperature difference between the external structure and the ambient induces a radiative cooling. Iteratively, reaching temperatures over the melting point can be avoided. Therefore, radiative cooling is used like a passive thermal control. The material selected to protect the integrity of the vehicle was found by Pseudospectral. This filters the aerospace material blocks. The best material for this purpose is stainless steel in a honeycomb structure due to the combination of low density, high tensile and shear strength, high melting point, and low thermal conductivity. With the trajectory, it is going to be explained some slides later, it is obtained the heat flow in the nose cone and leading edges of the wing. This data is introduced in a transient thermal simulation in ANSYS, and finally the result shows that the maximum temperature in the surface is 976 Celsius degrees during 37 minutes, which is less than the melting point of the material selected. As you can see, the winglets are the most heated part. Due to the specific shape of the vehicle, which is a lifting body, and the fact that the vehicle reaches the Kármán line, the most appropriate engine is a linear aerospike. An existing aerospike, the XRS 2200, has been selected. Also, this engine has the ability of thrust vectoring to steer the aircraft, which means there is an extra state variable in the control system for pitching and yawing the vehicle.
So I just want to define the cabin, taking into account the moderate time of flight, which is about 2 hours. We based the configuration of the cabin into two columns, 12 rows and 4 seats per row, which ends up summing up to 48 passengers plus 2 pilots. Fuel tanks are placed between the cabin and the aerospike engine, and the total vehicle length is reduced and is obtained iteratively, taking into account these fuel tanks and also the mass requirements for the mission. Talking about mass, the cabin places a high portion of the total mass on the axial axis of the vehicle, reducing the decreasing the moments of inertia of the vehicle and also increasing the control over the center of gravity all along the flight. Once all of this data is available, we can establish a dynamical model. This dynamical model will represent the system behavior in the real world so that its results can be optimized and yielding a desired specific performance. Obviously, a trade-off between accuracy and complexity has to be reached. It is important to obtain results, make conclusions, and further iterate the initial design without great time investments. Once the dynamical model is available, we further proceed to compute an optimal trajectory. This optimal trajectory is defined as the one minimizing fuel consumption and also time of flight. And the problem was solved using a non-linear programming formulation of it without the constraints on altitude, acceleration, etc. The results, which in particular were obtained using the interior point optimization algorithm, are shown partially here now. And despite the discrete and numerical nature, as you can see, they saw the need of a really vertical and fast climb while maximizing the cruise phase at a Kármán line altitude. And the final re-entry and landing phase take advantage of the vehicle momentum to reach the range specification. We also proposed a guidance, navigation, and control architecture to enhance the vehicle performance under model dynamics noise. For the guidance part, we use a standard polynomial regression of the optimal trajectory. In the case of navigation, we propose an extended Kármán feature for sensor fusion and state estimation, and the tracking control problem was closed using an LQR PID controller, which is shown to stabilize the vehicle dynamics under these kind of negative feedback control loops. I just want to go real quick around vehicle architecture in general, just as a wrap up. We studied two main things, the exterior configuration and the interior one. In the case of the exterior configuration, obviously aerodynamics, a visual appeal, and also an aquatic inspiration to it led to a really ambitious lifting body prototype In the case of the interior configuration, though, we acknowledge the commercial nature of the vehicle, and we decided on a much more standard first-class commercial configuration, also to increase the passenger safety and control.
All right, to sum up, the designed vehicle meets the constraints posed by the challenge, as well as our initial additions. And as far as concerns maximum time and distance, acceleration limits, and safety for all the passengers that it is transporting. Both subsonic and supersonic flight conditions have been taken into account in the exterior design in the wing, and an aerospike engine has been selected as the optimal propulsion system for this case. Finally, the trajectory was optimized based on minimizing time and fuel consumption. On this slide, you can see the final model that we created for this vehicle. And this has been Project STEINER. Thank you for your time and attention. And if you have any questions, please let us know.